3. Atlas didn't just leave our solar system, it left behind clues in its dust that challenge what we thought we knew about cometary material. As this interstellar visitor raced through space, it shed an envelope of gas and dust, unlike most comets formed in our solar system. The way its dust scatters light, the mix of gases coming off its surface, and the unusually high levels of carbon compounds all suggest a chemical makeup that doesn't fit the planetary rules we've come to expect here at home. Unlike typical comets, where water ice dominates near the sun, 3I Atlas's coma is rich in carbon dioxide and other volatiles, and its dusty halo interacts with sunlight in unexpected ways, hinting at a birthplace far from our own cosmic neighborhood. This isn't just another passing comet. The dust it leaves behind is a record of ancient conditions in another part of the galaxy, and it may force us to rethink how cometary material forms and evolves across star systems. While 3I Atlas left our Earth's neighborhood and is now slipping back into the vastness of interstellar space, the trail of dust and gas it left behind tells a story quite unlike most comets born here in our own solar system. Astronomers have used some of the world's most powerful telescopes, including Hubble, JWST, and ground-based observatories, to analyze the material streaming off this ancient visitor, and what they've found isn't merely typical dusty debris. For one, the chemical makeup of its coma, the cloud of gas and dust surrounding the comet shows abnormally high levels of carbon dioxide, CO, compared with water ice. Data from the James Webb Space Telescope revealed a CO2 to water ratio far higher than what we usually see in comets native to our solar system. This ratio stands among the highest ever recorded, suggesting a volatile mix of ices that responded strongly to solar heating as the comet passed nearer to the Sunday. The dust itself appears to include larger grains ejected at varying speeds, and its reddish-tinged haze, similar to what's been seen in other interstellar visitors, hints at irradiated organic compounds processed over billions of years before arrival. Combined with the fact that small dust particles responded slowly to solar radiation pressure, the overall dust behavior differs noticeably from typical solar system comet dust streams. This unusual dust profile suggests that 3ITLS may have formed in an environment with colder temperatures, different ice lines, or prolonged cosmic radiation exposure conditions, unlike those near the Sunday. Such composition challenges assumptions about cometary dust rules derived mostly from local comets and forces scientists to reconsider what kinds of interstellar materials might be drifting between the stars. In essence, 3I Atlas's dust isn't just debris, it's a chemical fingerprint of a distant world shaped over eons and delivered here for fleeting study. When scientists compare 3I Atlas with comets that formed around our own sun, the differences become clear, and they reveal how unique this interstellar visitor truly is. Most comets in the solar system come from regions like the Oort cloud or the Kuiper belt, areas where icy bodies formed from the leftover material of planet formation. As these comets approach the sun, heat causes water ice to sublimate, driving the familiar jets of gas and dust that form the coma and tails. The relative abundance of water ice to other volatile compounds is a typical signature of these bodies. 3. Atlas, however, tells a different story. Observations from the James Webb Space Telescope and other instruments show that its coma is dominated by carbon dioxide, CO, relative to water. In fact, the measured ratio of CO2 to H2O is far higher than what is normally seen in solar system comets, at least 8 times greater than expected for typical cometary activity. This suggests that 3I Atlas formed in a very different environment, likely where CO2 ice condensed more readily than H2O. Another key difference is the way 3I Atlas has responded to billions of years of cosmic radiation. New research indicates that exposure to galactic cosmic rays may have significantly altered its outer layers, transforming carbon monoxide into high levels of CO2 and creating an irradiated crust that standard solar system comets do not typically show. This means the material we see now has been heavily processed over eons of interstellar travel, a kind of weathering that is unlike what comets here experience. Finally, while solar system comets often begin outgassing water as they near the sun, 3I Atlas showed delayed and distinct activity patterns with emissions and dust shedding occurring under conditions that wouldn't normally drive similar behavior in local comets. Taken together, these differences underline that 3. I-Atlas is not just another comet, it's a chemical time capsule from another star system shaped by conditions and processes far removed from those that govern comets born around our Sunday. What makes 3I-Atlas more than just another fleeting visitor in the night sky is that it offers a rare window into material from another star system, something we otherwise can only imagine but rarely observe directly. Unlike the comets that have formed inside our solar system, where planets, moons, and asteroids share a common origin, 3I-Atlas was forged in a completely different stellar neighborhood and has traveled through interstellar space for millions or even billions of years before reaching us. That makes it a messenger from afar, carrying with it chemical fingerprints of conditions that existed around another star. Because 3I-Atlas is only the 3rd confirmed interstellar object ever detected, its passage is an extraordinarily rare scientific opportunity. Most comets we can study are bound to the sun and formed with the same broad chemical mix as everything else in our solar system, but an object from outside challenges those assumptions. By comparing its dust, gas, composition, and behavior with that of typical comets, astronomers can test whether the processes that shaped other planetary systems are similar to or fundamentally different from our own. Even now, as 3I-Atlas continues its escape back into interstellar space, the data it left behind is being analyzed by telescopes and observatories around the world. Each measurement, from the proportion of carbon dioxide in its coma to the structure of its dust particles, adds a new piece to a puzzle we're just beginning to assemble about how planetary systems form and evolve across the galaxy. In the end, 3I-Atlas matters, not because it threatens us, but because it expands our understanding of the universe, reminding us that our solar system is just one of many, and that the cosmic story is far richer and more varied than we once believed.